So I'm Keith Parrish. I work for NASA at the Goddard Space Flight Center out of the project office there. I'm the commissioning manager for Webb, which means basically for the last few years I've been planning out all the details, all the engineering support, all of the different activities that actually occur during the 6 months of commissioning. So overseeing all of our planning for commissioning, and then ultimately taking those plans and working with our flight operations team and turning all those plans into actual operational procedures and products.
And once Webb launches, once it's off the Ariane 5 rocket, where does control transfer to initially?
Yeah, so we are all of the flight operations for Webb are done out of the Mission Operations Center at the Space Telescope Science Institute in Baltimore, Maryland, and that's located on the campus of Johns Hopkins. And yeah, so what happens is we launch. About 3 minutes into the flight, the Ariane 5 will release its fairing. That tells the Webb spacecraft to start turning on its transmitters. And then here at the MOC, we call it the MOC, the Mission Operations Center here in Baltimore. Webb will start sending out data, and our NASA TDRS satellite system will pick up that signal and relay it here to the MOC. So we'll actually start seeing data from Webb roughly 3 or so minutes into flight once that fairing comes off. So that's actually pretty soon. For a lot of spacecraft, we actually get to see data, and that's what we're really looking for. And so control of Webb happens really fast right before. Now we don't command Webb. We don't actually tell it to do anything for almost an hour. And what happens there is about 27 minutes into flight, the Ariane will release us into orbit. And what happens there is Webb will sense that separation and kick off a whole nother set of programming, which means, deploy your solar array, make sure you're pointed at the sun. Eventually, we get Malindi ground station, which is in Kenya on the east coast of Africa. That ground station will also start receiving our signals just like TDRS. And then what we do, we establish a command link via that ground station. And what that means is we can actually start sending commands up to Webb. So we'll do that roughly about an hour into the mission.
What are some of those first commands? I know the solar array is pre-programmed, that's supposed to be automated, but what are some of the first commands you're going to be sending up to Webb?
Yeah, so the very first thing we're going to do is we're going to tell Webb's communication equipment to be ready and start to do what we call ranging operations with our ground station. So we tell our communication equipment to go into a certain mode that lets Malindi again to actually what we call ranging, which is Doppler data, coherent Doppler to range. And what that does is that tells our ground controllers, specifically our navigators, our flight dynamics group, they're going to start building data, which is telling them how fast Webb is going and in what direction. So we're really looking for many hours of ranging data, and over those hours between the Malindi ground station and the Canberra ground station in Australia, and then ultimately the ground station in Madrid, which is our deep space network that NASA uses for all of its, a lot of its missions. Between all of those different ground stations tracking us, providing Doppler information and then other information, our navigation team will be able to tell they'll be able to say exactly how fast we're going and what direction. And we need to know that so we can do some small correction burns about 12 and a half hours into the mission. So that's the very first thing we tell Webb to do. Other than that, everything else, we do some software. We do some we upload a little bit of software, some patches. For an ephemeris, we actually upload some data files that Webb can start using. Maybe a little bit later than that, we actually start doing we command it to start doing some checkouts of some other equipment. So it's actually a pretty quiet time. None of the commanding is dramatic. It's pretty routine type of commands.
So if I understand the timeline correctly, on day one, the critical events, obviously the launch and separation, that has to go well. You got to get the solar array out. and then there's that correction burn around 12 hours after launch.
Yep.
Can you just walk me through the purpose of that burn, why that's so critical, why it has to occur at that time?
Right. So we want to go to L2, and so we need a really, we need an exact velocity, pretty accurate velocity to get into the orbit that we want. Which means you want to kind of, we want to go to L2. We don't want to go past L2. But then again, we don't want to slow down so much that we actually would, not actually come back towards Earth. But so a very, very specific amount of velocity that we need. The Ariane 5 will do an outstanding job. I mean, they'll put us pretty much on the money going to L2. So what we do is, based on all that tracking data that we get from the ground, tracking us for a while, we will fire our propulsion system. And really what we're talking about is meters per second of velocity change. So we're really, we're thousands of we're kilometers per second of velocity. And what we're doing is just small tens of meters per second. So it's almost, it's really, really small velocity changes that'll dial us into going to L2 exactly right. So that's our first thing, is to really correct out any of what we call launch vehicle dispersions, which means how accurate does the Ariane 5 deliver us. They have an outstanding track performances of putting spacecraft right on the money, and we expect them to do that for us too. But we do expect some residual error, and that's what we take out with that first correction burn.
If I understood correctly, the Ariane is actually slightly undershooting on the way to L2.
Yeah.
Is that correct? And then this burn.
That's it. Yeah. Yep. So normally when exactly right. So yeah, so that's good. Excellent point. I should have brought that out. So it's kind of a subtle detail, but that's awesome. Yeah. So when we tell Ariane to always don't put in. I guess if we told Ariane to send us exactly to L2, what would happen is they would have a dispersion curve, which means they could give us too much velocity or not enough velocity. They would try to shoot for the center. So what we tell Ariane to do is to underburn a little bit, so that we always have to make up velocity. We would never have to turn around and sort of brake, take off energy ourselves. And the reason we do that is if we have to turn, we only have thrusters on one side, which is the spacecraft side. So if we needed to brake or take out velocity, we would have to spin the entire observatory around to where the telescope would be pointed back at the sun. And we don't want to do that, of course. So for safety reasons, for thermal reasons on the telescope and the instruments, and also because of our solar array, we would have to off point it from the sun. We tell Ariane to intentionally underburn a little bit, and then we're going to make that up with our onboard propulsion system. So that's a really, really good, a really cool point to point out, is that subtlety.
Yeah, I know there's, I've seen the estimate of around 10 years of fuel life on board Webb. Mm-hmm. And I know the astronomers, every hour of observing time is priceless for them. Yeah. The 10-year estimate, is that a conservative estimate? Is that right in the middle of that curve that you talked about? I mean, if the Ariane 5 puts you exactly where you need to be or want to be, could that 10 years be stretched? And if so, like how much?
Yeah, the 10 years comes from a bunch of things going sort of the wrong way for us. So it'd be like Ariane performs really, really poorly, and we have to make up a lot of velocity. And when I say a lot, I'm going, instead of 20 meters per second, maybe 70 meters per second. It's still tiny amounts. And also we're delayed. We can't, for some reason, do the burn soon. So we take all that into account. Ariane underperforms a lot. We, for some reason, can't do our burn at 12.5 hours. We have to do it sometime later. All those, and then some other conservative things. All those things together, we still can make a 10-year mission life. So that kind of gives you an idea of our, again, mission life as far as fuel amount, 10 years of fuel. So a lot of conservative estimates go into that 10-year fuel life. And again, based on what we expect Ariane to do, based on other things sort of being nominal, we would exceed that by a significant amount of years.
what's a significant amount if everything goes perfectly? I
Yeah,
know
it's
I don't want to pin you down to a number. Is it 15-ish? Is it
yeah, I would
20-ish?
never want to, it's you know, you get into subtleties of whether we still have we still need oxidizer for our station keeping, and then we have our mono propellant for just attitude control and momentum dumping. So you get into some subtleties. Which one of those tanks would go dry first? Again, if you're outweigh, if once you get into 20 years of oxidizer, then you say, well, maybe I'm just running out of propellant for my station keep. But I don't want to get into those subtleties. I mean, you could easily get to 20 years of fuel life plus if everything comes up, comes up heads or however you want to say it. You could easily get there to 20 plus years.
I think a lot of astronomers would be really interested to hear that. Once you have the trajectory after the launch, once you know how much fuel you're burning on the way to L2,
Yeah.
how soon will you know if that 20 years is within the realm of likelihood?
Well, it's a lot of different things. So obviously we would know based on right away. Once Ariane gives us their data within the first couple hours of the flight, we're going to go into a posture that will reflect what they actually did. So we are planning to burn at 12 and a half hours. And and once we get that data back from Ariane, we're going to know real fast on how critical that 12 and a half hour mark is. We train and perform and we're ready to do it at 12 and a half hours. But then again, you go into a little bit of so we'll know Ariane is like number one. So once Ariane puts us where we think they're going to go, we're going to have a really good idea of how much mission fuel life we're going to have. I'd say once we get our propulsion system checked out and we get the spacecraft in the first couple of hours, that'd be sort of our next mark where we're going to give us a good idea of, what time we're going to burn. When I say exactly what time, I don't mean like a day later or even half a day later. I mean like 12 and a half, 14 and a half hours, somewhere in that range. We'll dial it right in. So yeah, the fuel life is interesting because we don't like to say, wow, you could get a couple decades of fuel. I mean, we always wanted people to be cautious about the fact that, we have a lot of really cutting edge instrumentation on board, a lot of electronics, and that always presumes that equipment is also still working. You may have a lot of fuel, but you may not have a functioning set of instruments, so to speak. So, but yeah, fuel, we're going to work to maximize that, and we're pretty confident we will.
Yeah, I wanted to focus a lot on what happens on launch day, and we've heard quite a bit about the 29 days of deployments throughout New Year's and
Sure.
and January. But I did want to, while I have you, if you could talk a little bit about that, what happens on day 2, and then run through
Sure.
the sun shield and when different things deploy and what you'll be watching for.
Yeah. So like I said, our very, very first objective on day 1 is to do that burn. That'll be sort of a nice little moment to relax a little bit because we're going to L2 and obviously all of our subsystems, our engineers will be learning a lot about how Webb is performing on orbit and the environment that it's always been designed to be in. So I tell people Webb really wants to be in orbit because it's tough to deal with on the ground. It's a very cumbersome observatory to handle on the ground. So being in 0G, being in space, we're real excited about that. And our subsystem engineers are going to be spending most of that first day and even to the second day just checking out their subsystems and getting things working. When we get into day 2, a little bit of a quiet day. We actually start turning on some of our main computer. We continue to activate different hardware, but the main thing we're going to do on day 2 is we're actually going to get our gimbal and antenna assembly deployed. And again, that's our high data rate antenna. We don't really have to do it, but that's a nice place to do it on day 2. It's a little bit of a quiet day. Day 3. It's sort of at the end of the day 2 is when we do our next what we call our mid-course correction 1B. So we have another mid-course correction there on day 2. So when I say, I guess I'm getting my days, I got to make sure I'm very, very clear on here. Day 0 is launch day, and that's when we'll do our mid-course correction. Day 1, we'll go ahead and get our antenna out, and then day 2 is when we'll do our second mid-course correction, which we call 1B. Again, depending on how 1A goes, we may not have to do 1B. We just don't know yet. Or we decide we're not going to do 1B until later. We got a lot of flexibility to do that second mid-course correction sometime. But right now it's scheduled for day 2. And then we're done. We're kind of done all our mid-course corrections. Then we go into 14 days of deployments. So the very first thing we're going to do on day 3, again, 0 being launch day. Day 3 is where we start our sunshield deployments, and that's what we'll do that day. Is we'll do our 2 big pallets. We call them our front and rear UPSs. We'll get those down. The next day we're going to do our deployable tower assembly, which is getting the telescope up away from the spacecraft. And what that does is that frees us up to actually all of the material for the sunshield is actually stowed in that area, or some of it is. So we need to get the telescope up away, and then that will allow us to pull all that material out. So that'll happen on day 4, where we start doing our day 5 is where we start doing our mid booms and extending those. So that all takes over, between getting the sun shield out. Then we go into tensioning operations. Once we get the sun shield out, that's great, but then we have to sort of tighten it up. And all 5 layers have 6 different points around there where they're connected up, and then we'll pull on cables in each one of those corners and actually tighten up the sun shield. And that takes a few days to do that. So roughly, depending on how it goes, roughly day 10 or so, we'll get into what we call our telescope deployments, where we'll deploy our secondary mirror, which is the tripod-looking thing. And then ultimately, we have the 2 wings of the main mirror that have to be deployed. So that's what I call our primary deployments. All along the way, we're doing a lot of releases and launch locks. We release our cryocooler assembly. We have some additional radiator shades that we have to deploy and get those out. So there's a lot of little, what I don't want to call them small deployments, but there's other deployments that don't quite make the headlines like the sunshield does. So that takes us through the first 2 weeks of the mission. We're finally deployed. We got everything out. However, our 18 mirror segments, which is, the 18 mirror segments they're put into a launch position, which means they're kind of snubbed down tight against some stops for launch. So the next 10 days, so say day 15 through 26, 25, roughly 10 days, our telescope team will actually start moving each one of those 18 segments off of their stops. So they'll start wiggling around those 18 mirrors, get them off of their launch position, and that's a very tedious process because they're gonna, they only move them a really, really tiny bit each time. So that takes about 10 days just to do that mirror operation and move those around. So a little bit quieter, a little bit slower pace of action as they do that. Again, more spacecraft activities. We're bringing up higher data rates. We're continuing to raise our communication equipment data rates up during that time. And then once they finish with the 18 mirror segments, we will do that last mid right around day 29 is when we do that last mid-course correction, which we call MCC2. So remember, we have 1A, we have 1B, and then 2. And then that ends that sort of what we call that 29 days of high anxiety or terror, or whatever you want to call it, on the edge. I think it was the name. But so we're done at that point as far as moving things around. The other thing that's happening during that first 29 days, especially after the sun shield comes out, is the telescope is cooling rapidly. We actually start cooling down the telescope from, down to its cryogenic temperatures, and it's dropping fast in those first 29 days. A lot of software is uploaded for the instruments. The instruments are supported, begin to support operations in that 29 days too. They just don't quite make the news as much as those other major activities. So that's the first 29 days. and I'd say the first 14 days are pretty, nonstop excitement. And then once the mirror guys start working with the 18 segments, of course, that's their exciting time. So they would probably differ with me there, but they'll be busy the second 10 days of that.
That burn at 29 days, is that the burn that puts you into the orbit around L2, or does that come sometime later?
Yeah, that's sort of what we call that's what we call like our insertion burn. Like the first two burns get you going to L2 with the right velocity, right direction. And then that last burn, the 29-day, we call it the insertion burn. But again, we're really talking a small puff of the end of the propulsion system at that point. Again, we're not even sure, we may not even have to do that burn. We may just, based on everything that's going well, we may delay that burn and do our first, we may not even do that burn until we do our first, what we call our station keeping burn. Every so often we have to do a little burn, even when we're at L2, just to stay at L2. So it's kind of like a station keeping burn, and we may not even do it, but we're planning on doing it, but we may not even have to, given how good 1A and 1B go.
I've heard about these deployments for years now, and I'm just wondering how long. We obviously know Webb had its genesis in the 90s in many respects, but how long have your team been working on this commissioning timeline, and how many times have you practiced it? Do you know it in your sleep? Okay. All this stuff.
Yeah, I mean, I'd say the commissioning timeline, which is 6 months of like I said, the first 29 days is pretty cut and dry. Sort of the second part of that 6-month commissioning timeline is all about the telescope, getting the telescope aligned and phased up, and a 2-month process, very tedious process. And then you get into the back half of that 6 months is really where the instruments are doing their calibration activities and bringing all the instruments up to. So it's kind of like there's 3 phases of getting deployed, getting the telescope aligned, and then finally the instruments do their calibration activities. On top of that timeline, we're also going through what we call our fine guiding activities, where we're bringing on our fine guiding system, which consists of our fine guiding sensor provided by Canada, interacting with our spacecraft attitude control system. So, we have Hubble-like pointing. We can point very, very accurately and precisely, but that's quite an interactive system between our fast steering mirror, our fine guider, and our attitude control on our spacecraft bus. So we're also doing that on top of that 6 months of activity. Again, we're also cooling down. So lots going on. A lot of different subsystems are working to get themselves up and running and characterized. Planning for sort of that 6-month phase has been in works for many, many years. I mean, it's the sort of the overall sketch of how that's going to go is almost sort of there's not a whole lot of variables to it. You're almost locked into these steps. What I would say is where the details have come in a couple of different places. Number one is making sure you have all of the commanding ready to go. Actually the software ready to go, the ground systems, the flight operations team, and all the sort of the details that go along with that. That's probably been intense now for about 4 years. For the last 4 years, that's been really, really fine tuning those details. So you asked about our timeline. I mean, our timeline is down to the minutes. I mean, we kind of know every minute of every time of activity, what we're actually doing. So it's really, really detailed. And obviously it started from, broad brushes to really, really fine details. So you get into, you take that timeline and you start rehearsing it. And rehearsals come in all different, they come in all different flavors. We've done what we call small team rehearsals, where we just have the deployments team, rehearse actually deploying their hardware on a simulator. We have lots of simulators that can simulate what actually happens, and they practice on that. And then we actually have what we call full team exercises, which are here at the Mission Operations Center in Baltimore, where we bring in the entire spacecraft team, the entire flight operations team, the deployments team, and we run through deployments here. And we've done that, multiple times. I don't want to say a number because I would get it wrong, but I know it's more than my fingers. Of actually what we call full rehearsals here in the Mission Operations Center, where we don't know if Webb is on the ground or in space. We don't know. To us, it's in space, and we're deploying it. So we've done that multiple times. And again, the other key thing is our deployments team, more important than these simulations we've done in the mock, they've deployed the real hardware on the ground. So they've deployed Webb 3 times in the test environment. So it's those same engineers that have deployed Webb on the ground in testing and virtually in all of our simulations. It's going to be the exact same team here, hopefully next week. When we get off the ground, it'll be the same engineers here deploying it for real for the first time in space. So lots of rehearsals. A huge amount of those rehearsals is devoted to what we call contingencies or anomalies or things just not going right. And we've rehearsed just about every degree of bad thing that could happen to make sure that all of our, because that's really, I'd have to say that's probably devoted most of my team's time for the last probably 2 years, is saying, hey, we got this great plan. Now let's break the plan and see how we can recover. So everything from a deployment not going right. We even have I even mentioned MCC-1A and how important that is. We even have a plan for if the mock isn't available to do the burn. We have a backup mission operations center down at the Goddard Spaceflight Center. So we've rehearsed how to hand control over to that backup center so they can execute the burn. And then we go into, well, what if our personnel aren't available? So we even have backup personnel down there that can execute that burn. So that's the level of detail we've gone into contingency planning, all these different scenarios from human factors, people, COVID. COVID's a big thing. What if we lose our team to illness? That's a very big thing we've been thinking about. And we thought until recently we didn't have to worry about that anymore. But in the last few days, we've been sort of pulling out all of our COVID plans on how we would deploy Webb with maybe a few of our team members quarantining. So that's a big reality for us. And then a lot of our other anomalies are, the hardware just isn't behaving correctly on orbit. What do we do now? And everything from this didn't release correctly to we don't have confirmation that it released correctly to it's being stubborn. It's not moving. It just doesn't want to move. So we rehearse all those different scenarios also, not just on deployments, but all other areas of the spacecraft too, something not quite going right. And we call that our contingency planning. And we have rehearsed quite a bit of things going bad. And the team, and I always tell people, it's not really about the team solving a Rubik's Cube of a problem. It's really about making sure we have all the tools, the software, and the products ready to go so the team can use them if we do have some type of anomaly. So that's the more important. Again, we have a full-scale simulator of the sun shield out at Northrop Grumman on the floor. If our team needs to look at that and see it, and so that's the type of contingency planning that we have, that we've rehearsed and we have ready to go for next week.
And that's the shimmy, and that's one of your contingency options, right? Is to kind of shake the observatory with thruster
so
inputs.
I think some of our slang has got out into the public recently. So we do have what I would call our degrees. Let's just talk deployments for a second. If we're talking anomaly on a deployment can be everything from I didn't get a verification that this thing moved all the way to something didn't move at all. So there's all these degrees. And the deployments team and the spacecraft team and our system engineering team, we got a lot of bells and whistles. We got a lot of tools in our toolbox to be able to deal with all levels of different things that may not go exactly right. However, there are what I would call some extreme intervention and things like shimmying and twirling. And to describe those a little bit, a shimmy is our ability to shake Webb a little bit using its onboard propulsion system. We can actually impose some shaking into the system So we call that a shimmy. We can also twirl the observatory, which means we can spin it at a rate to where we can put some static forces and help put some loading on an area that may be a little bit of stubborn. Um, we also have the ability to use the attitude control system, specifically the propulsion system, to be able to move Webb back and forth rapidly, so we can heat and cool a specific area that may be giving us some trouble. So we call those sort of like shimmy, twirl. I think we call the back and forth fire and ice. Again, I always tell people, if we're using those tools in our toolbox, we're not having the best of days. But we didn't want to launch without those tools in our toolbox. We said, hey, is there anything we could possibly do on orbit to do some of these things? So in the last few years, we did make some modifications with our attitude control system to be able to do these shimmy and twirls. I mean, it's not something you spec in a design spec for an observatory to do these things. But in the last couple of years, we did a lot of studies and said, hey, can the attitude control system and the propulsion system do this? After some careful study, they came back and said, yeah, we can twirl you and we can shimmy you. And we said, let's do it. Let's make sure we have that tool in the toolbox. Let's never get it out. Okay. Let's make sure we never have to get that tool out, but we have it there. Again, in case. And we feel really good about all the other tools in the toolbox that I would say, if we're getting that tool out, the small set of pliers, I'm okay with that. That's something we're going to work ourselves through. If we're getting out the big hammer like shimmy and twirl, then yeah, that's something that's something we don't want. That's a tool we don't want to get out.
Before I let you go, I know I've taken a lot of your time, but you talking about all those tools that you have available, your team has available to respond to something that's off nominal or unexpected. You've had a lot of time to put that toolbox together. I mean, do you think you've thought of everything humanly possible? Or are you afraid of any unknown unknowns or out there? How ready is your team?
Unknown unknowns are the big one. Yeah, I mean, unknown unknowns are the really big one. I mean, we, trying to figure out, and it's, I know your audience is fairly technically minded. So, trying to figure out what can go wrong is an inherently unhuman activity. That's just not how our brains think. I mean, you've heard everything from, lack of imagination. We all remember Apollo 1 fire and things like that. So we try to do that systematically. We don't like sit around and go, what bad thing can happen? We really like to do we like to take imagination out of it, and we like to really look at every different mechanism, every different part. And when you get down to that level, that's where you can kind of go, what could go wrong at this part level? And that's how we sort of create our toolboxes based on that. And then we work that part level up to the system. And then when we get to the system, where we say for something like Webb, we go a major deployment failure, for the life of us, we can't figure out how to make it fail except for an unknown unknown. Because that's how much we've designed the system to be robust enough at the part level, at the system level, where we really can't come up with a scenario specifically where we say, if that happens, we're not deploying. We just can't figure out what that is. So that would be in that category of unknown unknowns. And that's why we have a broad toolbox. Again, things like shimmy and twirl are there for those unknown unknowns. So we try to take the imagination out of it, because our imagination will always fail us. So we try to be as robust as we can. And I can confidently say that when it comes to the capabilities that we built into Webb to be able to overcome anomalies, we've left nothing on the table, or we've left it all on the field, so to speak. When it comes to that. So I think the last thing that we've done is really we've augmented our ACS a little, attitude control system a little bit, and we have a very, very rehearsed team. We have very, very methodical processes, and again, we're fully electrically redundant. We have redundant windings in our motors. So yeah, like any deployment, we would be very, very concerned about snags. And I think when it comes to the membranes, when cables, those are not deterministic systems. things that are flopping around and not tight, not structure. So that's where we really put a lot of attention into making sure that we don't have membranes going in any place where they could snag, or even cables snagging on something. That's one thing that we pay a lot of attention to. So kind of a long answer to sort of you get into these hypotheticals, and that's a really, really tough place. Like I said, I will say confidently that we've tested these deployments on the ground. They're almost a little bit more challenging to do on the ground because of the amount of offloading we have to do. But then again, Webb's never been in this environment, and Earth, it's never rode a rocket before, even though we've tested it much wider. We've tested it to conditions much worse than the rocket will do to us. But again, it's on those unknown unknowns that we've tried to do as best we can to have the tools on board to deal with.
How thick is that contingency book?
Well, we live in an electronic age, right? So we don't print it out. We've probably identified, again, a contingency is a reaction to an anomaly. We have, I don't like to quote a lot of numbers, but we have, on the order of 100 or so different, contingency responses that we've created for different things. Again, there can be little minor things all the way up to shimmying and twirl. So there's about 100 of those. Again, it's kind of hard to quantify from a thickness of the book or anything like that.
Well, Keith, thank you so much for your time, and good luck with the launch and commissioning. I know your job's not over on Friday. You have a lot of work ahead of you, and we'll be watching. Thank you.
Yeah, awesome. Yeah, we're very excited, and we're ready to go.